So yeah, we have this very simple circuit here with just a battery, a switch, and a resistor. And right now the current is 0. And so there's no magnetic field. Now, if we close the switch, we know we're going to get a current, and then it'll create a magnetic field into the board. And so this loop rule, we're going to have the EMF minus this, the changing flux. Remember, that's going to create an EMF by Faraday's law. And that would be minus L di dt. Oh, wait, minus IR. So this term here, we have neglected that in some cases, like when we first started talking about circuits. Like a circuit like this, you flip the switch, and we just ignored that term. And we were very justified in doing so, because the inductance of a circuit like this would be basically nothing. Very difficult to calculate because the magnetic field varies, so it's hard to calculate the flux, but pretty insignificant. That term is. It's only significant when you include an inductor like a solenoid, for example. And then we have a significant inductance, and that is called self-inductance because it's a current in this circuit that is, so yeah, we're building up a current, and that current that we're building up is affecting the circuit itself. But say we have, let's get rid of this one. Let's say we have another circuit here, let's say a light bulb or something. And there's no power supply. So if we flip the switch here, now nothing would likely happen here. But imagine you had an extremely sensitive device that could measure, say, a current. So a light bulb would not be the best thing to do. But say we have a very sensitive current meter here. When we flip the switch, we're going to detect a current here. And that is, the reason is that, we flip a switch here, we're creating a current, which will create a magnetic field around the circuit. So it's not just inside the loop. This current would probably be coming out of the board here. Because this is the closest branch. A current going down, that would create a magnetic field out of the board. And so when you flip this switch, that creates a magnetic field in this loop. And that would drive a current in this loop. And again, let's practice Lenz's law here. Initially, there was no current. So what direction is the current going to be in this loop? Clockwise or counterclockwise? Well, initially there was no flux in this loop. And so now there is a flux. So the change in flux is out of the board. And so the induced current has created a flux into the board. That would be a clockwise current. And this current created would then influence this one because that would create its own magnetic field, which would affect the flux over here. But again, these effects are usually fairly small. We probably just ignore that. But these two circuits, even though they're not physically connected, they do interact with each other. Affecting a current in one will change the current in the other, or it'll create an EMF in the other loop. But again, the effect would be very, very small unless we kind of design it to be large. So and the biggest factor though is like how close they are to each other. So let's say that, let's say we have a coil. Like we have a cylinder here, and we wrap this coil around a bunch of times. And this one is hooked up to a power supply. So we call this the primary coil. And so we have a current. And let's say NP is the number of turns in the primary coil. And so next to it, we place a secondary coil. That's not hooked up to a power supply. We have like a voltmeter or some device, whatever. Could just have a resistor here. There will be a current in this one. The direction doesn't matter. It depends on how you wind. If you start looping behind and go around, or the other way. So you can make the current go in either direction. So let's call this the primary current, and this the secondary current. And so if we have a current here and that creates a magnetic field around it, it's essentially a solenoid where it's, just horizontal down the axis, but then when it gets to the end, it spreads out. So we're going to have a magnetic field, and we can see that some of these lines cross through this secondary coil that has a number of turns NS. And now if we just had like a battery here and created a current, there would be a flux in this coil, but it would not be changing. So nothing would really be happening. But if we have an alternating current here, the current is constantly changing. So this magnetic field is constantly changing. And so we have a constantly changing flux in our secondary coil. And that changing flux will create an EMF in the secondary coil that will drive a current in the secondary coil. And what we can say is that, say the EMF in the secondary coil we can say, shouldn't be too hard to believe that the EMF in the secondary coil, the reason that it exists is because of the changing current. Let's mix them up. I'm going to try to be consistent with the currents. But the changing primary current is what creates the EMF. So the more rapidly the primary current is changing, the greater the EMF in the secondary coil. So hopefully that's a reasonable thing to say. And to make an equation out of this, we can say that the EMF in the secondary coil is equal to M times the rate of change of current in the primary coil. Okay, so that M is called the mutual inductance, also measured in henries. So I go over for a single coil, we had the EMF was L di dt. Here we have EMF in the secondary coil is M di p dt. And how do you determine mutual inductance? We kind of don't. It would be extremely difficult to do because these magnetic field lines are spreading apart. So it would be a very difficult calculation anyways. We'd have to find the rate of change in flux in the coil, but the flux, we'd have to do that surface integral, taking the direction into account with a dot product. So generally speaking, that's a rather difficult thing to do. It would be something you'd probably just measure. Now, mutual induction is actually an extremely important thing. So here, this is just the basic idea. And again, the mutual induction, it would also depend on the number of turns in the coil. So that's definitely a factor. But I want to look at an application of mutual induction that is rather important. There's different ways you could draw this, but I'm going to draw a rectangle. Like a square. Let's say this is made out of iron, which is ferromagnetic. So it can be very strongly magnetized. And let's say we have an alternating power supply here, and we wrap it around. So we have like NP turns in the primary coil. And on the other end, so again, this is just like, you can actually make one of these, although I do not recommend just making one and plugging it into an outlet, because you have to be very careful about that. But here, this is our secondary coil. That can be hooked up to something. Let's just say there's a resistor there, or some device that has a resistance. Now, this is an iron core, and that greatly affects the magnetic fields. So basically what happens, like if you have a solenoid, magnetic fields would just be along the axis of the solenoid, but then once they leave the solenoid, they spread out. But what this iron core does is that kind of directs the magnetic field lines so that they form these loops. They tend to stick inside the iron, because iron is a very magnetic material, and it can be magnetized very significantly, and so that kind of guides these magnetic field lines to form these closed loops. And so we can make an assumption that the flux through any coil on either side is the same. So let's call that phi 1. This would be the magnetic flux through a single coil. And again, that single coil anywhere in this device, whether it's primary, secondary side. And again, the coils all have the same area. And we're assuming that none of the magnetic field lines escape. So like every magnetic field line passes through every loop. So to a very good approximation, this is going to just be constant through every loop in the device. And so let's apply Faraday's law. So remember Faraday, the EMF is we don't really care about that minus sign, but it's basically equal to the rate of change of flux with respect to time. So yeah, it's a changing magnetic flux that creates that EMF. And so let's look at this primary coil here. So the EMF in the primary coil, that's, let's forget about the minus sign. The EMF in the primary coil is going to be the change of flux of the primary coil. And so that would be like the flux through the primary coil is a number of turns in the primary coil times the flux through a single coil. We can take the NP out. So we have d phi 1 dt. And in the secondary coil, kind of the same thing. Okay, and now based on our assumption that the phi 1 is the same everywhere, we can set these equal to each other. And so what we get is that the EMF in the primary coil divided by the number of turns in the primary coil, that's equal to d phi 1 over dt. That would be equal to the EMF in the secondary coil times the number of turns in the secondary coil. Or we could rewrite this and look and see specifically. There's something called the turns ratio. I never remember what ratio it is, primary over secondary or secondary over primary. I don't think this book mentions it. It doesn't really matter, just a vocabulary type thing. But well, let's just do the EMF in the primary coil over the EMF in the secondary coil is NP over NS. And this device here, this is a very simple example of something called a transformer. And mentioned this before, that there used to be a big debate when electricity was kind of new. And Thomas Edison was one of the leading scientists working on that. And he believed very strongly that we should use direct current to transmit energy. And there were others that said we should use alternating current, and alternating current won. And for very good reasons. Basically, but the main reason is the existence of transformers. Turns out alternating current is actually more dangerous than direct current. So that was like why Edison didn't like it. But something like a transformer does not exist for direct currents. It requires this changing flux to happen. So if you have a direct current, like say you have a current going through a solenoid, you have these constant magnetic field lines, nothing's going to happen. And so what you can do with a transformer, let's solve for the EMF in the secondary coil. That would be the EMF in the primary coil times the number of loops in the secondary coil over the number of loops in the primary coil. And again, this is very easy to fix. So let's say that this is 120 volts here, because that's what you get from an outlet. If you have a device that say wants 15 volts, so for whatever reason this device has to have 15 volts to operate it, well, you got 120 volts in your outlet, so what do? You design a transformer that will convert this 120 volts into 15 volts. And like say this is our device. So we want 15 volts in the secondary coil. And again, so when you're designing the device, you would build a transformer into it. So you can just pick that turns ratio to convert 120 volts into say 15 volts. And there you go. And so it allows us to have this standard where you can just have like everything uniform. At least we're lucky that that's the case. Some countries, different parts of the country actually have different results when you plug something into an outlet. That's a really horrible planning, or more likely just a complete lack of planning. I imagine they just had like individual companies have their own standards and the government didn't regulate it. And so now your devices, you have to be careful what you plug it into. It might not behave properly, or you could damage it by plugging it into like the wrong voltage source. So it's very good to have a standard. Everywhere in America is 120 volts. Actually, transmitting power is a little more complicated. We use like this 3-phase wires where we have like 3 wires are all 120 degrees out of phase. And by combining them in different ways, you can have like 120 volts or 240. And so some outlets in your house are probably 240 volts. Those are things you'd plug big appliances into. But generally speaking, everything is 120 volts. And So yeah, you can design any device just knowing you're going to plug it into a particular outlet and it'll behave as expected. But another very important application of transformers, so let me find a picture. I've got a nice picture in a different book that shows, but it also is important in transmitting energy. So we talked about like Joule heating at I squared R, where, let's find this picture. The higher the current, the more energy wasted. Where when we're in a lab dealing with these circuits, we just have a power supply and those little wires, we couldn't care less about that Joule heating. Actually, maybe we could. We can overheat things and fry them, but the energy lost in the wires themselves is pretty much insignificant. But I think about like where's the closest power plant to where you live, the energy is probably traveling at least several miles before it gets to your house. And so that energy loss can be very significant. And it's more efficient to transmit energy at a high voltage. So I'm just looking for this, okay, found the page number. So yeah, we want to transmit energy at a high voltage because it is more efficient. But, yeah, like here's an example of a much more sophisticated transformer right there. You might have seen something like that. But yeah, so you want to deliver energy to your house from a power station. But for safety reasons, high voltage is dangerous. So we don't want the power plant itself working at a very high voltage. And you definitely don't want, like, generally speaking, in those power lines, that could be like 300,000 volts or something. You definitely don't want that coming into your house. And so the idea is we want kind of a relatively low voltage at the source and lower voltage at, so like here's the source where we produce power. We want low voltage here, and say this is your house. We want a very low voltage here, 120, but we want a very high voltage in between. Like a very high voltage to make it more efficient. And so we use transformers. And the transformer can be used, you have a primary and secondary. You can increase or decrease the voltage as you see fit by adjusting I erase the equations, or the equation for transformers. Let's see what that even was. I forgot. I can start out this way. So yeah, so you can, this turns ratio, which is just the ratio of the number of loops on the primary and the secondary side, you can make that raise or lower the voltage. So like coming from the power station, we'd have what's called a step-up transformer, which would make a very high voltage. And then we deliver it to your neighborhood maybe. And then we'd have a step-down transformer. That's still pretty high, but then another step. So like the step-down transformer, then we could kind of move it, to like different areas. But then you'd have another step-down transformer that would bring it down to 120 before it gets to your house. And so kind of a nice picture here of like the power transmission. So we have the power station, and it's like a sequence of transformers that can raise and lower the voltage, so we can transmit power very efficiently and also safely by lowering it or having low voltage at the source and at your house or the neighborhood, a very high in between. And so transformers, it's hard to imagine how our society would work if transformers didn't exist. It'd be very hard to transmit power. And then, you know, for devices that want to use different power supplies, that could be complicated as well. Yeah, I think for a computer, that like if you have a laptop, they've got that wire and then like a box and then another wire. I think the transformers in that little box there. So yeah, so transformers, very, very important application of mutual induction. All right, so are there any questions on anything? I'll stop recording.